Hello friends, we are continuing with our data compression algorithms. Today we are going to discuss about one of the very important and popularly used compression technique, which is called Huffman encoding technique or Huffman compression technique. It is followed by the technique which we have discussed in our last class, that is run length encoding, RLE. This Huffman encoding technique is more popular compared to that RLE encoding technique because it gives higher compression ratio, higher compression accuracy compared to our run length encoding technique. But these two techniques are mainly applicable for reducing the large text files or the large string files. So Huffman encoding has been developed by a very famous mathematician. He is David Albert Huffman, and it is one of the lossless technique. Actually, where the information is no information is lost in this technique, and Huffman technique is such a technique where we can reduce the file size, which is in a much simpler way, in much better way compared to the other technique. And Huffman has several variations in future that will be applicable in various research purpose. Like there is a version of Huffman, adaptive Huffman, which is a more advanced version of Huffman technique, obviously, which gives a better results compared to our general Huffman technique. But today we are going to mainly focus on the basic Huffman technique. So Huffman technique, I am just directly going into the example, which will be easier for you to understand this technique. And then I will discuss about the various characteristics of Huffman technique. So the example that I have given, I have already told this Huffman technique is also suitable for the compression of large text. So suppose one small table I have shown here. Here the number of the different characters has been shown in the first row, A, E, L, N, O, S, T. And here the frequency. What is frequency? Frequency is nothing but a redundancy of the characters in the text, or you can say the number of repetition of the same character in the text. So here I cannot, it's not possible for me to write 45 times the A character. That's why I have represented the entire thing by the help of this chart or table. So that means the A character is repeated in your input sentence 45 times, E character 65 times, L character 13 times, and so on. So if we apply RLE technique for this one, it will also compress your data, but if we, instead of RLE, if we apply Huffman, it will give much better accuracy compared to RLE technique. Now these are the very basic algorithm of Huffman. So Huffman, the first objective of applying the Huffman algorithm is to build the Huffman coding tree. So Huffman coding tree is nothing but a binary tree. If you know the data structure, then binary tree are one of the very famous tree by which we can organize or we can organize the data in a very quick fashion, in a very efficient fashion, reliable fashion. It's one of the very famous tree. So this is a binary tree. Huffman tree code tree can be represented in the form of binary tree. So binary tree is represented like a inverted tree structure where root will be at the top and different children and branches will be at the bottom part, right? So the first node is the root node, which has various children. This is left child and this is right child. In the same way, if this is the parent node, then these two are the children of this parent node. So in this, these are grandparent of this node. So there is a relationship in the data structure of the binary tree. So here we actually using this binary tree concept to represent a Huffman tree, right? So in binary tree, one logic will be there. A binary tree must have either 0 child or 1 child or 2 children. Now this Huffman tree, if we look at the data that we have already represented in terms of chart, this is a sort of characters which has been repeated multiple times in our text. Now the first logic to build an Huffman tree, which is nothing but a part of binary tree, we have to shuffling this data, and we are trying to apply a sorting operation on this data. That means we have to shuffling this data and rearrange this data into a ascending to descending order, right? That means from from small order to the large one in terms of frequency. That means the letter which has less number of frequency will be the first one, and the letter which has most number of frequency will be the last one. So if we rearrange this one, shuffling the data and rearrange this one, L is the less amount of data which has a less number of frequency, and E is the highest number of frequency data, and in the same way the others mid of the data will be rearranged in this way. Suppose there are two data coming with the same frequency, then it is first come first serve basis. Okay, there is no rule to rearrange this data. You can rearrange the data at any order or any fashion. Now second step, how to build, I'm just trying to show you how to build a Huffman code tree, a Huffman binary tree. Now we are trying to add the first two data. We can say the smallest data and the next to the smallest data. We are trying to add these two and make a basic children. So if we will add 13 and 18, there will be 31. A new node has been created where 13 is the left child and 18 is the right child, right? So 13 will L and 18 will right child. Now 31 is a new node. So here 31 was not there in previous case, 31 has come as a new node here. Now we will again run this reshuffling algorithm and sorting that fashion. So how we can again run this reshuffling algorithm? We add this 31 with the previous order except these two, right? Now if we sorting this one, then it will be S will be the smallest one, 31 is the middle one which has come as a new node, and the rest of the nodes has been organized as a previous fashion. In the same way, we will do the next step. We will again add the smallest and next to the smallest node, that is 22 and 31. Add together, and after adding these two, it will be 53. When it will be 53, the left child will be 22 and right child will be 31. You can get the same organization in this figure. 53 is a new node, left child is 22, right child is 31, and in 31 there is again left child, right child, which has been already made in the previous case. Again we reshuffle the thing and again make an ascending order of this data. So again we are adding the first two numbers, which is the smallest and next to the smallest numbers, and we will get a new node, that is 90, right? So if you notice here, so we will get two different tree, but while we will make our final Huffman tree, it will be the one. It will be one Huffman tree. How we will do that? It will, we don't need to do anything extra. It will do the process. The process will do it. So 90 will be organized as a highest frequency node at the right hand side of that one, and 45 is the left child, 45 A is the left child, N is the right child. Now again we will reshuffling it and arrange in a ascending order, and then again add the first two nodes 53, 53, that is 106. Again reshuffling it and adding as a sorted order, right? So 65 is the smallest one, 90 is after that, and after adding this 53, 53, 106 is the new node has been made. So in 106 there are 53 first node left child, and this 53 will be the right child, and that 53 has again a new combination of tree. So we will simply do the same thing. Here a new node has been received by adding this the first two smallest node 90 and 65, and we will get a new tree with a new node connection, that is 155, where 65 will be the left child, 90 will be the right child. 65 will be the left child, 90 will be the right child, and that 90 has its own subtree. So in this fashion, and we will add the last two subtrees together. Now these two left nodes are left. We simply add these two nodes and we will get a new node, that is 106 plus 155 is 261, and this 106 will be the left child and 155 will be the right child of that new node 261. This is our final Huffman tree. This is the first step of an Huffman coding algorithm. Now the second step of Huffman coding algorithm is very simple step. Second step said that each and every edge will be represented by some weightage in terms of 0 or 1, because in digital we are using either 0 or 1 to represent information. So either 0 or 1. Now Huffman said that you will given weight of the left edges as 0 and you can give a weight of right edges as 1. So we will do that. Each and every left edge, if you look at the tree, each and every left edge contains a weight 0 and each and every right edge contains a weight 1. Now if you see, each and every character will be represented by some sort of combination of 0 and 1. How we have made this one? We have directly made this chart from looking this tree from top to bottom. First, if you are seeing the character A, where is the character A? There is the character A. So this character A will be represented by, if we start from root, we are actually counting the number of weights that we will need to reach into the character A. So if this is a root, 1 we will need to reach in this node, again 1 we will need to reach in this node, and this 0 we will need to reach in node A. So here total weight 1, 1, 0 will be needed to represent a character A. Here A, S, L, O, T, all the nodes, all the last nodes, or you can say in data structure terms, these are the leaf nodes, okay, which does not have any children, right? So these nodes are represented by some sort of characters. So in the same way, how we can represent E? We can represent E starting from root, again count the weights associated with the edges to reach from root to that particular node. So E 1, 0. E will be represented by 1, 0. In the same way, how we can represent L? 0, 1, 1, 0. L 0, 1, 1, 0. N 1, 1, 1. N is 1, 1, 1. So in this way, we actually gathered the number of weights collecting from starting from root to that particular node and make this new table. There must be some advantage of using this table. Actually, we have already done the compression. So this is the final table where we can check whether our compression, Huffman compression, will successfully work or not. So in this table, you will see these first two rows I have already shown in the last table, which is a representation of each and every characters by some new set of 0 and 1 string combinations. So new set of 0 and 1 string combinations. And here the A will represent by how many characters? 3 characters, 1, 2, 3, 3 numbers. And E will represent by 2 numbers. L will represent by 4 numbers. N will represent 3 numbers, and so on. And these character frequencies, these are the old representation of the input string that we have already shown in our primary table. There is the original text representation. This is the original text representation. Now we are trying to calculate what will be the size of the original text representation and what will be the size after compression. So again, for sake of simplicity, we are assuming here 8-bit ASCII character system, suppose we are using. Now each and every character will be represented by 8 different combination of 0 and 1s. Now here A repeated 45 times, so total A needs 45 into 8, 135 bits. E represents 65 times. This I am telling about from the original text point of view, original text file size. A repeated 65 times will be represented by 130 bits. L represent 13 times will represent by 52 bits. In this way, the total number of frequency will be 261. The total addition of all the bits will be 261 multiplied with 8. Each and every character will be represented by 8 bits. So here 45 times A will be represented by 45 into 8. 65 times E will be represented by 65 into 8. Total we actually adding all these 3 and it will give 261 into 8, the same operations. Okay, you can multiply 8 individually with this number and then adding it, or you can adding all the repetition and then multiply with 8. The same result you will get. The result, the size of the file you will get is 2088. When 2088 bits you will require to represent the file size in original fashion. Now we will check how the Huffman algorithm helps us to compress that files. Here each and every character will represent by a new set of numbers. A represent by 3 bits, E represent by 2 bits. So again we will do the same operation. 3 into 45, 135. 2 into 65, 130. 4 into 13, 52. 3 into 45, 135, and adding all these combinations we will get 696. So you can imagine or you can calculate that this is the original file size, and after applying a Huffman coding compression scheme we will get the reduced file size of 696 bits. So it's a huge application, you can say, in Huffman, and it gives a better result compared to RLE compression technique. So this is all about the Huffman compression technique, and in the next class we will discuss about other compression algorithms like LZW, and I also want to discuss about some of the disadvantages associated with the Huffman technique, and in the next class I will discuss about it. Thank you.